the recording. Okay, so chapter 19 is kind of the chemistry of carbonyls. Really, you guys kind of already learned how to prepare them and do, I believe, reduction and oxidation reactions. That's probably from chapter 12. What else did you guys learn in terms of previous chapters, I guess? Acylation, I guess, technically, is also a carbonyl formation. There's been a wide variety of reactions that you guys already learned, right? But this chapter kind of focuses specifically on what's called nucleophilic addition, right? So you guys probably already learned in lecture, right? But kind of the brief generalized reaction, right, is if you have this, some nucleophile, right? Give it that, right? Yeah, okay, this is just a second. There you go. So they're called nucleophilic additions, right? The one you guys previously learned were reactions of alkenes, right? Whatever this is, right? And this was an electrophilic addition because the whole way this worked was you had some sort of powerful electrophile, right? So in nature, like in terms of their nature, it's based off the electrophile, right? You're adding the electrophile to your nucleophile. Same thing for like electrophilic aromatic substitution. It was all powerful electrophiles. So these are nucleophilic additions because now it's kind of based off the strength of your nucleophile, and you're really just exploiting the strength of the electrophile here. So simple enough. Basically, all these reactions are literally just nucleophile attacks at your carbonyl, right? That pushes up, you get your O minus. So this kind of depends on what's it called? What kind of conditions you are, if you're gonna get O minus or if it's already gonna be protonated. But in this case, since I just have a strong nucleophile, it's probably going to be okay to have O minus. We have our two groups here. We can call these R groups as well too. So this expands. R can be H, R can be two alkyl groups. It could be whatever, right? And then some sort of workup, right? So I'll just say H plus, and that gives you alcohol plus your nucleophile, right, etc. Now kind of the difference here compared to in this chapter, right, is that you have a kind of specific nucleophiles that form a kind of different, I guess I would call them intermediates. They are technically compounds, but the main purpose for a lot of this chemistry is protecting group stuff, right? That's the reason why people create acetals or whatever. It's they don't want to have a carbonyl react in a certain reaction, right? So you could protect it, do your other chemistry, deprotect it, and then you get your desired compound or whatever that might be. By the way, did you guys learn about Yilid's, what's it called? The Wittig reaction? Have you guys finished that?
No, we haven't even covered it. We didn't even start it.
Oh, okay. So how many nucleophiles did you guys get up to? I mean, I'd hope at least oxygen and nitrogen.
We got up to amines and Wolfkisson.
Yeah. Okay. Cool. All right. So that'll be fun. We could spend most of our time because a lot of people always have trouble with the mechanisms here. But I personally think they're some of the easiest mechanisms because they're literally just a repetition. If you guys see what the repetition is, you'll never really mess this up. But they are long, right? I guess that's what scares people, is that they're long. So okay, let's start with acetals then. Actually, let me just do one problem just to kind of show off one point here, which is this is 19.6b, right? So you have this plus HCl right? It's in an equilibrium with this halo alcohol or whatever you want to call it, right? Really the main thing that I just want to point out here, right, is you just have to be, I guess, wary of whatever conditions you are, right? And in a lot of these reactions, right, mostly the oxygen and I believe the nitrogen nucleophiles, and I guess the sulfur too, because sulfur is basically it's analogous to oxygen, right? You're going to be under acidic conditions, right? So for the most part, all those mechanisms, right, they're going to start off with protonation of your carbonyl, right? Which makes sense because if you protonate it, it's going to put a positive charge on the oxygen. Oxygen is going to withdraw electron density from your carbon, right? Which is going to make that carbon more electrophilic, right? So that's why a lot of these are acid catalyzed for that reason, because it just helps in terms of the reaction. So just kind of draw out the bond here. Right, so we could start off with our protonation. Goes here, I'm gonna go downwards. We have this protonated. H plus, right, well now it's as simple enough as your Cl minus is just gonna attack. Right, and all of this stuff with the acetals, amines, and amine, right, it's really just constant nucleophilic attack, deprotonation, like, you know, then this is repeating that process basically. Okay, so Cl attacks there. Oops. It goes up. You get your product, right? So now really the difference between this, really HX or really H, I can call this anything, right? Whether this is A minus, is that this can be like a OR group or something, right? And that would be your acetal reaction. And then if you have it, if you have like something like what is it, glycerol, I believe, right, or a diol, right, then you could do what's called cyclic acetals, right? But the process is all the same, right? So let's do an example of a mechanism. Yeah, so the whole reaction is reversible. I'm not going to really draw out those reversal equilibrium arrows when I do these mechanisms. I don't know even if the book does. I think they do. But it's just something here. Let me actually put up an example so we could just review why it is kind of irreversible. That's not irreversible, reversible. Start with, what is this? 19.8A. Well, that one's kind of easy. Let's do B instead. I mean, they're both kind of similar, but it's fine. Okay. So first you have H2SO4, right? Then you have an excess amount of ETOH, right? And then you have minus H2O, right? Let's zoom out for now. But so generally these are kind of what you expect in terms of a lot of this carbonyl chemistry, the conditions, right? So in terms of, right, what this means, right, is first you have, you know, in their brackets is H2SO4. So what does brackets mean when things are in brackets?
It's a catalyst.
It's a catalyst, right? So the real purpose of the H2SO4 is to provide a proton, and eventually that proton will be gone back to the acid at some point. The ETOH has two purposes. What are those? So one, yeah, it's a nucleophile, right? So this is, you know, any sort of alcohol, right, can be your nucleophile here. And then it has another purpose here as well. think about what the reaction has to be in, right? Would there be anything else to make sure everything's mixed together, or is ethanol enough? So what would that make ethanol? It's a solvent, right? So you could also kind of think of this as a, well, it's not exactly a solvolysis reaction, but it's solvolysis-like in the terms that your nucleophile is also your solvent, right? So yeah, you don't have any, usually your nucleophile is also your solvent, right? And then the last part, right, this minus H2O, this kind of is what has to do with the equilibrium, right? Is really, if you control how much water is in here, you could, push it forward, or, basically it'll be a process backwards. So this is called the Dean-Stark method, right? I believe that's what it's called. And basically, usually when people are doing these kind of reactions with carbonyls to create acetals, amines, and amines, etc., right? There's something called a Dean-Stark apparatus, which basically removes water from the reaction, right? And this kind of basically, I'll ask you what kind of thing does it exploit in terms of pushing the reaction forward? If you remove something from the product side to push the reaction forward, what's that kind of called? That principle, Chatelier's principle, right? So that's really, a lot of chemistry is exploiting Le Chatelier's principle in order to push reactions forward into completion, right? And then literally, if you decided to reintroduce water to all of these, which we'll go over to identify like acetal and amines, hydrates, all these bonds, they're basically OCO or NCO bond, or NC, I should say. If you literally just introduce water or, slightly acidic solution to them, they will literally go backwards to the original carbonyl. And that's why it's important to make sure all the water is gone, so you actually get your, final product there, right? And that's why this whole thing is kind of, in terms of reversibility, it just depends on, how much water and acid you have, right? It's not exactly favorable, right, to create acetals. If you think of delta G stuff, right? You're essentially taking one molecule plus two molecules, right? And then it's going to make one molecule, right? So entropically, that's unfavored, right? And that's T delta S. So that will, change your value of delta G in a way that's going to make it non-spontaneous, right? Hemiacetals, though, when you guys will see in carbohydrate chemistry, whenever you get to it, that's kind of a little different because you actually don't have a change in entropy there. But yeah, that's the main reason a lot of this stuff is in equilibrium, and not like you need to remove the water in order for it to go forward, because it's not exactly very favored. But it works. That's one thing. People figured out how to make it work, right? So okay, let's start off with kind of this process here. It's gonna be a long mechanism. We're gonna be doing a bunch of these. So start with our carbonyl down here again. So our first step is gonna be what? Protonation, right? So H plus there. Now we have our protonated carbonyl, right? Now we have made this essentially a more powerful electrophile, because remember, essentially you want this, that, so that builds up the partial positive charge on the carbonyl. Right, then their next step is, now this is very electrophilic. You have a good enough nucleophile, so you have your nucleophilic addition, right? So next step. And this is the part where I just mentioned, I guess you could have, what is it, TOH. You could have like equilibrium arrows for most of these steps, except the only step I wouldn't put it as is after the water is removed. But And technically, everything is in equilibrium with each other in these reactions. But I don't think either Professor Biscoe or Boson will, well, actually ask them if they want the equilibrium animals or not. If you have to do a mechanism. Okay, so this attacks, this kicks up, right? It's literally just following where the electrons are going, right? The first thing is protonation, right? Then the next thing is the electrons from your oxygen, right? Going to be attaching there. That is constantly kicking up. It doesn't really matter where you get the proton for, because you can't really prove where it's coming from, right? One thing to kind of understand in terms of organic chemistry is that mechanisms, there's a reason they're all proposed mechanisms, right? I don't know if you guys ever noticed, I don't know if Klein actually says proposed, but they are proposed. Right? No mechanisms are kind of what can be argued against, right? It's usually, especially in papers and stuff, it's just like you can't prove everything happened that way. You can, you could provide enough evidence to propose something, right? But you're not like 100% sure that's exactly the way it proves. So in terms of proton and deprotonation and all that stuff, you can't tell me that it was the water or it was a protonated alcohol, right? It could be anything, right? The main thing is understanding it's the protonation that's happening, right? So I think they both accept H+. I mean, you could ask to confirm if he wants you to show like a protonated, H3O or protonated alcohol in this case. But in terms of simplicity, I always just stick with H+. And as long as your electron movements and stuff is good, I think they'll probably be okay with it. But like I said, just confirm with him just to be sure. Okay, so our alcohol attacks, it attaches, right? Just get your bonding correctly here. So one, you have your, oops. We're gonna, I guess I'll just curve it downwards. We have OH here, right? Now we are bonded to O. So we're bonded to the oxygen, right? I've seen people mess this up a bunch of times, right? Just make sure you're tracking what you're bonding stuff to, right? So here we have this, right? That is oxygen that's bonded. It's ET on one side. It's going to be H here, and it's going to be a positive charge there, right? Now we'll just go downwards, kind of this circle, right? Next step, right, is once again, we're still in acidic conditions, right? And essentially the main goal is to try to create, oh, I just realized it actually does give you the product. So probably should have shown that there. Yeah, most mechanisms questions will always give you the final product, so you have an idea of where to go.
Is this the same textbook as ours?
Yeah, this is 19.8 from your textbook. Klein 3rd edition, the main textbook. Okay, so now next step, right, is essentially we want to create 2 OET groups there, right? So we're going to have to basically get this alcohol group gone, right? So once again, we're in acidic conditions. Alcohol groups, right, can be protonated, turned into water, and leave, right? So that's what's going to happen next, right? We'll see another H+ here. Oh, actually, yeah, it doesn't really matter. Technically, I could have grabbed the proton off that H+ over there, but it's fine. Actually, I'll do that instead, technically. That way, I can already skip a step in terms of deprotonating that. That should be OET. Yeah, that saved me a step. Yeah, I don't know actually if he did it this way. So sometimes, I don't know, depends on your professor. Like sometimes they'll deprotonate. Let me kind of highlight what I did here, right? So this group, technically what you could do is just deprotonate it first, then protonate your OH, right? So that would basically be 2 steps to do that. So what I just did was I just kind of did an internal proton transfer because once again, you can't prove that that didn't happen, right? I don't know if Bisco did it that way as well. And you could ask him if that's okay. But the main thing is that understanding it's just all it is proton removal and proton protonation, right? So deprotonation or protonation. In this case, it just hopped over kind of, right? Okay, so now basically what happens is your reformation of your carbonyl, right? So once again, let's kind of just trace back everything that happens. First step is protonation. Next step is nucleophilic attack. Then it's basically creating a water group, right? And then it's reformation of your carbonyl, right? And then you get your, basically electrophilic center again, and then the attack happens all over again. So at this point, just put some electrons here. That kicks off, right? So water now leaves. Let's say minus H2O, right? And now we have your reformation of your carbonyl. And then your next step is literally a repeat of steps. What is it? Well, not the protonation step, obviously, but your nucleophilic attack and your deprotonation of that group. So once again, ETOH comes in. Now we have 2 bonds here. Just make sure you bonded it correctly and leave it like that. Should be plus, right? And then next step is just deprotonation or whatever. I guess we could just use ethanol since there shouldn't be any water at this point. And you get your final product.
So we can't use the water that left?
I mean, you couldn't prove to me that it's not there either, right? Right, it wouldn't be wrong using the water. It's just, I didn't use it because if we're doing this in a way that's collecting the water outside of the reaction medium, right? Essentially, there shouldn't be water left after it leaves, right? So in terms of I don't think there might be trace amounts left, which could act as a base, of course, right? But that's why I just chose ethanol there because, it'd just be easier that way. But like I said, technically it could be any conjugate base. It could have been HSO4 minus, right? That's technically there too, right? That's why all these, as I was saying with protonations and deprotonations and all this kind of stuff, you can't prove what really did that, right? There are certain things that are, act as bases like water or the ethanol and the HSO4 minus, but you can't tell me that you knew which one it was. I just picked ethanol because at this point here, right, I already removed water, right? So it wouldn't make sense for there to be really more water if we were, using like a Dean-Stark method here. There's a generalized mechanism. Actually, I don't know if it's in this book or forgot, or if a professor kind of wrote it out. See if I could find it. It was like using basically HA. I don't think it's in. I'll see if I could find it, but it was it was like HA. I don't know if it is in this textbook, but it like basically generalizes every single one of these reactions. And like if you kind of have that down, you could always figure this stuff out. Okay, so let me let you guys try a cyclic one. So let me just go over this once again, right? So let's label this stuff, right? So first is the protonation, right? We could call this a nucleophilic attack, right? We could call this protonation, deprotonation, right? Or you could think of it just as an internal proton. I'm just kind of curious though, in your notes, did he do an internal proton transfer or did he deprotonate it and then reprotonate it? Kind of curious.
Bisco, sometimes, or like he's been doing the intramolecular protonation, whatever, but
Yeah.
he usually shows that wiggly sign with a H, if you know what I mean. Yeah, he just introduced that last lecture.
Wait, like this?
Yeah, exactly. For that, he uses that for protonation and deprotonation.
Oh, so he doesn't show the arrows, right? Just to kind of make it.
Yeah,
Oh, yeah. Okay. I don't know if
that's
I
why
don't know.
he introduced that last lecture. So
Yeah, I don't know if you're allowed to do that on your exam. That's just for him to like, so he doesn't like he can spend more time teaching the chemistry and not have to worry because like
we
protonation.
can actually for
Oh,
Bisco we can on the exam. Yeah, he
well,
does it on the exams.
Yeah, because that's good. Yeah, because it's like protonation, deprotonation. It's like it's just it's so simple. It's just like why waste time doing it? But okay. So anyways, yeah, we could consider that. Then I would say this is Carbonyl formation, right? And then you have your nucleophilic attack again, and then your deprotonation, right? So yeah, we could actually put this as the H plus like that. So yeah, it's literally, it starts off with, what did I write? I write D there. It should just be H as well. Same thing I'll write here then. Right, so it's literally a protonation, nucleophilic act, rejumbling the proton. Then it's the carbonyl reformation. That's what I mean by CF, or carbonyl formation. And then once you get your carbonyl again, it's still very electrophilic. You get your nucleophile attack and your deprotonation, right? So it's literally about 1, 2, 3 steps, and then a repeat of steps, basically 1 to 2, right? So if you kind of always remember that like order, right? That it starts off with the protonation, then your nucleophile attacks, then you rearrange stuff to get your carbonyl again, right? And then another nucleophilic attack, right? So yeah, that's literally all of these reactions, right? If there was not excess, so like you mean the hydrate here? I kind of didn't really show the intro. I should have showed the intermediate, I guess, but so basically, let's try it here. You know what? For the next mechanism, I'll show it. So this is the hemiacetal, right? If you didn't have an excess, no, you probably would still go towards the acetal. The hemiacetal is at least open chain hemiacetals are extremely unfavorable, right? They're not exactly very stable, right? That's why it's just one of the intermediates. So you would basically, if you didn't have an excess amount, you'd probably just have a small amount of your product and you'd probably still have your original carbonyl, right? It's very hard to isolate the hemiacetal. I'm sure, you can do it. It's just, it's not easy, right? So yeah, I'll show that for the next step, I guess. I kind of forgot because I just do the deprotonation. Like it's kind of I guess in terms of your mechanism, it's important to know that structure does exist, right? So let me put some arrows here, right? They go that way. Well, I was saying earlier, Carolina, that it could be ethanol or HSO4 minus. It doesn't really matter, right? Just some conjugate base or some base that does the deprotonation. That's why he also, like I asked, accepts this minus, this tilde sign H plus or whatever, right? Because it doesn't really matter what deprotonates or protonates, just a proton transfer. Okay, let me let you guys take a a few moments to try this. This is the cyclic one, right? This actually, let's do D instead. It's a little bit more difficult. So it'll probably take a few minutes. Oops. So you have this. And you get, I'm just gonna put this as H plus.
The bottom is minus H2O.
Yeah. That was the same in the earlier example too, right? That just indicates a Dean-Stark method, so you're pushing it forward. Okay. This is one of those types that maybe you'll see on your exam. That's mostly just because it's like not as simple as the other ones. So anyways, yeah, take a few minutes to do that. do this. All right, so in terms of kind of trying to figure out what happened here, right, is you kind of want to just look at the final structure. So obviously, if you're given this on an exam, all mechanism questions, I always kind of see where what kind of things changes or added or et cetera, right? So here, right, so whenever you see this OCO, right, that is your acetal group, right? And it could be a variety of different molecules, but that OCO bonding is always an acetal, right? It doesn't matter what's connected here, right? That itself is the acetal group, right? And that means that if you have that position, that usually that's where the carbonyl originally was, right? So basically you could say that if you wanted to go a little backwards, right, would be that, let's draw over this final product, would be like this. This is the carbonyl, right? This bond would be cleaved, this bond would be cleaved, right? And essentially this is kind of what originated, right? And then if you look at the structure here, that's literally what you have. The only difference is you have alcohol groups. So really this is just an internal acetal formation, right? And it's just going to be, you know, each alcohol group coming in, attacking it, etc. Right? So let's go back and start the mechanism, right? Is now we know that basically these alcohol groups are just going to go in, form your product there. So we can start with the first step, which is just protonation, which I'm now going to use that for. Doesn't really matter which side you pick. OH. It's going to start off with the right side. Kick this up. Now, this is the part where you just have to make sure you draw your structures properly. Okay, but you could kind of just use that final structure and like, so basically you have, what is it? Here, here's your O bond, right? 1, 2, 3 carbons in between, right? So 1 second, just want to draw this properly. Actually,
Wait, can we stay with the structure that we already have and do the final thing in the end? I feel like it's gonna get confusing.
I mean, whatever's easier for you, just make sure your bonding is right, right? I'm actually just going to use the final structure. And this should be an OH here, right? And then the rest of the chain is still open. So that's how it would look. And we have an H over here. So this would be plus, right? So basically you have 1/2 of the ring at this point. So if you notice, all I really did was I kind of just used this portion, redrew that, and then have the rest still open chain, right?
How did it become closed though? I don't see that.
See this this arrow here, right? That's the bond that's happening, right? So here essentially is this is bond is that arrow, right? The other arrow is now this OH, right? This OH is this one, right? So that's literally it was an internal nucleophilic attack, right? And that's how you got one side closed. And this is still kind of your, I guess in this case, this would be your hemiacetal after we deprotonate it, right? So that's all that happened, right? It's literally instead of alcohol, an external alcohol, right? Like ROH or something, right? In this case, the alcohol group is already part of your molecule. So it's just attacking the carbonyl, right? Because we have the right conditions for that. Okay, let me just redraw that in white. Consistent. Thing is not working. Okay, we could just do another deprotonation and we get our hemiacetal, right? So our OH, once again, this OH was our original carbonyl, right? Now we have this. This is our hemiacetal, right? Now what are we gonna try to do basically? When we have the hemiacetal, what kind of main intermediate do we want to get to again?
Carbonyl.
Yeah, so you want to reform your carbonyl. What happened in H plus is we just deprotonated it, right? That's what the squiggly H plus is there for, right? So you had your protonated hemiacetal, now you just have your regular hemiacetal. So once again, hemiacetal group is any group that you have O, and then HO is the other side, right? And this could be any chain, open chain, etc., right? I mean, you could have, it doesn't matter what deprotonates it, right? That's why I put the squiggly there, because I wasn't sure how, what he uses for the deprotonation. And I hoped he would just, do something as simple as that, which he did. So the deprotonation arrows aren't really, I mean, they're important to understand, how the electron movement works, but they're just so repetitive at this point in the course, and like all of your orgo knowledge, you should be comfortable with those, right? So that's why we're shorthanding it. If you want like the full every little electron movement, I'm pretty sure the solutions manual will probably have that. But this saves you time in your exam, especially if it's allowed. Pretty sure boson allows it too. Those in boson's class might want to confirm that though. Anyways, so yeah, then let's just go downwards. We're gonna do another protonation, right? And we should just be copying and pasting these structures, but it's okay. One, two, three. Just gonna draw like this. 1, 2, 3. Okay. Now here, right? Remember that OR group that you installed right now is just part of the molecule. That still is what's going to reform the carbonyl, right? So once again, this is all just internal, right? The main difference between what we did now and what we did above, right? Everything is just internal. And we kick off water, reform our carbonyl. Should have enough space to draw it here. Okay. Okay, you have a plus charge here. And now it's literally just a repetition with the other OH group, right? So simple attack, kicks up. And now we have the OCO bond that we were trying to create before, right? In that product, this OCO bond, right? That's what we have. So if anything, at this point, you could just redraw kind of the product. It's going to be protonated. Right, so that got its protons back. This gained the positive charge, and it still has its hydrogen on it. No, it's just a simple deprotonation. Oops. Try to draw that a little better. Yeah. Boom. So yeah, all these reactions, I mean, most reactions in general, they always follow the same pathway. It's just the main thing that's different are the structures, but the chemistry itself is the same, right? In terms of electron movement and everything, that's all going to be the same, right? We could, if we label these again, right, starting from the beginning, is first step is, how do we label these again? So proton transfer, right? We'll put this in orange again. So call this PT. Then the next step is your nucleophilic addition, and another proton transfer, another proton transfer, right? Then your reformation of your carbonyl. So CF, reformation of carbonyl, I guess, whatever, carbonyl formation, whatever. Then your nucleophilic attack, and then another series of proton transfers, right? The double bond is over here, right? Is that what, that's when we, oh, sorry, nucleophilic addition should be this one. Oops. There we go. Guess I want to ask to see the electron movement of the very last step. I guess you could really just, doesn't really matter what conjugate base would be here. Technically we had, what is it? H2SO4. So I guess I could just use HSO4 minus. Missing a charge here. And then you just get your final product. Could have been water, could have been another molecule of this gigantic dialcohol. We had the diol, could have been anything, right? I mean, it probably wouldn't be water though, like I was saying earlier, but I don't think it'd be wrong to use water. So for that person who was talking about that earlier, it's not really an issue. But the main thing is if you don't have to show these proton transfers, you could just, indicate a proton transfer with the squiggly, or maybe if you write a proton transfer like PT, right? He'll understand what you did there, right? The main thing he's probably looking for is that the electron movements between the oxygens, right? The nucleophilic attacks and the carbonyl formation and all that. Just wants to make sure you understand that. That's the more important part of the chemistry, right? Protonations are simple. You just have something that protonates, or deprotonation is 2 arrows. Protonation's 1 arrow, right? It's just a repetitive kind of arrow movement that hopefully everyone understands at this point. Okay, so there's a problem because I decided and realized I don't think, I mean, that's why I usually do the in-chapter problems because I think both Professor Bozon and Bisco, they recommend problems from the end of the chapter, right? But I figured, especially since your last test, since you guys got problems from those end of the chapters or the recommended problems, I'll probably actually do some of those in these sessions as well. So there's actually a good one I saw here. Well, there's one where I want to talk about electrophilicity. We'll do that towards the end of the lesson. Let's do 19 since we're doing mechanisms right now. Let's do 19.58, right? What we're doing right now is just acetal formation, or hemiacetal formation, however you want to really look at it. Okay, this is a good one. Glutaraldehyde. Stick with the background here. This is something I might actually see that you would be something similar would be on your exam, because this is a good problem. So H3O plus, right? And you have OH there. So I'll talk a little bit. I want to let y'all try this for yourself, but I'll mention a few things to start off. And as first, what kind of functional groups do we have in the product? Well, in terms of this chemistry, what do we call the OCOH? But you're not wrong. That is technically an ether and an alcohol. But the OCOH, oh, oops. The hell do I? There we go. That's just OR, OH. What is that functional group called? Just talked about those. So if this is an acetal, there's two ORs, right? What's that intermediate in between? Hemiacetal. There we go. You have to be, you have to make sure you could identify these in a structure, because you might get a question where he gives you a hemiacetal or acetal, and he'll literally just give you water or H3O plus, and it's basically well, you're going to learn at the end of the chapter. It's the hydrolysis reactions for those. So it's literally the backward reaction, right? So, if you get that question on your exam, like in, those, what is it, question 3 or 4, whatever it is, and you're like, I don't know what this does. I don't know, like all you're really looking for is that OCO bond, right? And you're just going to reform a carbonyl. But anyways, we have 2 of those here, right? That's kind of the point I was getting at, that we have 2 of those bonds here, here, and here, right? And these are both hemiacetals, right? And in terms of our reagents, right? We only have H3O plus, right? So now when we did alcohols, it was always acetals and hemiacetals here, right? But when you have water, what is that called? When it's OH, OH. To hydrate, right? So basically what we're trying to really do here, right? If you think about it, right, is we are creating a hydrate, right? But eventually the hydrate, because when you form one of these hydrates here, right? One of them can act as, an alcohol, right? And basically react with your other carbonyl there, and then you get a hemiacetal. So that should kind of really give you a hint in terms of the mechanism. Is first, if we were to just identify where the original carbonyls were, right, it would be here and here, right? And that would mean if we broke this bond, we added an oxygen to this, right? So one thing in terms of difference in the structures, right, is that, well, actually, I should draw it like this. This would have been carbonyl, right? Also do a carbon count to check, right? 1, 2, 3, 1, 2, 3. So this was probably the original structure, and that means we added an oxygen some way or another. And that makes sense in terms of our reagents being, given here, was that we probably added an OH via hydrate formation, right? So I'll give you guys, take a minute or two to basically figure out, right? I mean, I kind of gave, I think, enough hints here. You won't be getting this many hints on your exam, obviously, but kind of where to start off the mechanism, right? So yeah, just to write that here. So hydrates. So these are hemiacetals. I'll just write it on the side for future notes. This is OH, OR. So this is acetal, hemiacetal. That is illegible. And which one are we missing? Oh, hydrates. This is hydrate, or it's also called a geminal diol. Geminal just means like, you have a geminal dihalide, right? It's 2 halogens at the same position. So this would just be a geminal diol. Anyways, take a few minutes to work on that. Okay. Hopefully that's been enough time. So let's start this little process here. So first, right, we could just simply protonate this. I'm just gonna do that. Oops. Okay, so we have that protonated. Now, once again, since our only really nucleophile here would be the water, that's what's going to happen next. I guess we can. Yeah, I'm just going to keep going downwards. It's a little bit easier that way. OH2. Right. And now you have your hydrate formation. Now we could just deprotonate this. Another proton transfer. Yeah, I should just write proton transfer underneath. That's usually what Boson writes too. So I'm just going to write PT here as well to indicate proton transfer. So anyways, now you just have your, sorry, someone was saying something.
Yeah. Can't the bond on, can't the O from the other side just take one of the H's and makes a neutral OH, and then you have an attack from the OH to break the double bond?
Yeah, you could do that too. Like I said, it doesn't really, like basically what you're saying is this is going to grab this, make that electrophilic, and then proceed with the rest of the mechanism, right?
Yeah.
Yeah, you could technically you could do that. It's just that in terms of like intermediates, you just want to show the hydrate and all that stuff, right? That's why like in the first one I kind of added that thing at the end, which was the hemiacetal, right? So here I just want to, and you probably would want to do this for your exam too, is just to make sure to individually show that you formed a hydrate at a certain point, then you did this kind of nucleophilic attack. But it wouldn't be wrong to say that, because the reality is this stuff happens at a kind of a picosecond scale, maybe a little slower, who knows? But you might be right. Like that proton transfer could happen, or like a proton transfer can happen from the water. Like you can't really prove. We know how the final product is, and these are just proposed mechanisms, right? But the logic makes sense there, right? This is a carbonyl. It grabs a proton, right? And basically this happens all within like picoseconds of each other, right? But I mean, if you want to draw it out and then ask him, because that's the main thing, it comes down to what they will accept on their exams, right? So you just want to confirm with him if that's okay. I just want to make sure I draw all the intermediates here, just for simplicity of everybody. Okay, so we have our hydrate here, right? Now we could basically just do that protonation. So if we did what's it called? Someone's asking, why kick out the water when you just added it? We are not going to kick out the water here.
That was just a reply to
Oh, okay. Yeah.
classmate. Yeah.
Yeah. So as why this? Yeah. Okay. What are we doing here? Another proton transfer, right? So I don't know who it was who said that before. If you did what they said, right, the internal one, you'd basically just skip this two and get directly to this intermediate that we have now, which would be this. Let's try to make that a little neater for y'all. So we'd automatically get to this, right? If we just did that internal transfer, right? So maybe I'll just put that as a side note here, right? Internal proton transfer here, right, would just lead you to this intermediate. Right. Now it doesn't matter which one of the alcohol groups attacks, they're both identical. That's what I'm not sure of, right? Because that's what I did in the first one too, right? I did the internal proton transfer because I just hate drawing this shit. But just confirm with your professor, right? That's the main thing, if he will accept it, because he also wants to make sure you understand the intermediates that form too, which is an important part. Because the thing with how, like, it's why all this stuff is proposed mechanisms is, but these intermediates were isolated, right? Whenever somebody did this reactions, right? That's how we know they're formed, right? Is because they were able to be isolated, and people could prove, okay, this thing formed at some point in this reaction, right? That's why it's important to have them. But it wouldn't be wrong going, to orange, right? Okay, and then from here, it's just a nucleophilic attack, right? So internal nucleophilic attack, doesn't matter which one you pick, right? Right. Now, if you notice your ring here too, right, you could do a little atom count, 1, 2, 3, 4, 5, and 6, right? And then what do we have at the top here? Right, if I remove this, let's draw the original product again. Original product was this. So if our oxygen is 1, and we go in a circle here, 1, 2, 3, 4, 5, and 6, and that OH is that carbonyl that used to be there. That's why I was saying breaking the bonds and seeing where the carbonyls and stuff like that can be very, very valuable tool, right? In terms of assessing mechanisms and what happened, right? Okay. Now we could just form our product. It'll just be the protonated version, really. So here. I do wonder if you actually even need to protonate that there. Now we actually have I'll check on that later. I just noticed now we actually have 2 formal charges there. Oh, actually, no, we don't. Sorry, that already had a positive charge. My bad. Never mind. It should be like this. Okay, cool. All right, and then just another proton transfer, right? And then someone asked last time. I'll show this one again, just to be clear. Right, so we could use water in this case. Those are just the proton transfer arrows, and you get your final product like this. Yeah, usually these intermolecular kind of questions, a lot of professors like asking them because anyone can memorize A plus B equals this and all that stuff. But like, so I was saying it's more important to understand the logic and the arrow movement, because the chemistry is always the same, right? Okay. So yeah, let's take like a 5-minute break at this point. So question for y'all is in terms of the nitrogen stuff, you guys got the amines, right? What about enamines? You guys did enamines as well. Okay, perfect. Other stuff is there. You guys said you did Wolff-Kishner as well. Okay, that's the hydrazone. Well, first, I would assume you guys probably learned the hydrazone thing.
Can you also go over a Wolff-Kishner problem?
Yeah, when we do, I just, we didn't do any nitrogen stuff. We're just making sure what you guys covered in terms of that. Did he do sulfur? Or no? Thioacetals? Did he talk about, because I know usually he teaches this for thioacetals, the book for some reason doesn't do it. I don't know if that's the one they use, or maybe they use 2 carbons. They use 2 carbons. But did he talk about, well, here, right? Did he talk about if you treat this with something like, I don't know, let's say N-butyl lithium, right? It's a strong base. It could deprotonate this, and you actually get a very well stabilized carbanion here. That he, I know usually, I think it's, I'm pretty sure it's Professor Biscoe that does that. I don't remember. But did he mention that about the kind of acidity of the proton and your thioacetals? That you could basically, if you have one there, right, that's the main thing, is if you started with an aldehyde and you have one there, right, you could deprotonate it pretty easily with a strong base. And it's going to be stabilized really well here. Then kind of forget it. He used to, I think he used to do it, because I'm pretty sure I learned it from him, or I forgot who it was. But yeah. I guess I'll just mention it now, that if you do have a proton here, right, it's a very good proton in terms of acidity, because when you have this carbanion, you have 2 sulfurs next to it, right? Sulfurs are huge, right? They can stabilize the electron density from the carbanion really well. So you have a, good carbanion there, basically, or nucleophilic stuff. Then you could, really react it with any electrophile. Technically, most likely, actually, the lithium might coordinate there. You actually would get Li here. But if he didn't mention it, don't really worry about it. All right. We still have a few more minutes. Let me just go get some water. Okay. Let's do nitrogen stuff. Yeah, lithium, aluminum, I think that terbutoxyhydride or something like that. I forgot the name. But yeah, no, it's just another source of H minus. It's more controlled than LAH. It's a lot less powerful. But it's essentially just a delivery agent for H minus, but it only does it once, right? So that's acyl chemistry, acyl chemistry. Now it's kind of more covered in chapter 20, right? So carbonyls is just generally aldehydes and ketones. Technically, they're still acyls too. Acyls is when you have basically some sort of electronegative thing. Usually it's derivatives of carboxylic acids, right? And they just make the carbonyl more powerful there. Okay, let's find some amine problems, I guess. So nitrogen stuff is similar as well. The main difference is that, well, I mean, I can ask you guys, in terms of what starts the mechanism off? Is it a proton transfer or is it a nucleophilic attack? Well, I mean, I guess it depends. It doesn't really matter. I mean, I didn't view your lecture recording. I don't know if you started off with the proton transfer. Either mechanism would be fine. He did, yeah. So I used to do that as well. I think because it doesn't really matter. I know the book likes to talk about having a nucleophilic attack, right? And the reasoning they give is that it's more nucleophilic, blah 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 blah. But I remember I used to always start off with the proton transfer, and I think it was for bosons class. So this just to be clear for those who have boson here, right? He always starts off with the nucleophilic attack, right? That's why I remember when I was doing it once during the recitations, right? And people are like, "Oh, weren't you supposed to have the nucleophilic attack?" And I was basically trying to explain to them that it really doesn't matter because the main thing is getting the carbonyl amine, right? But boson apparently specifically wants to make sure you do the nucleophilic attack. So Bisco doesn't care. It doesn't really matter. For boson people, you have to start with the amine attacking first. Somebody was going to say something.
Yeah, weren't you gonna like perform the actual mechanism for the above example you drew out?
Oh no, I was just mentioning it. I mean, the mechanism is pretty simple, right? It's just an N-butyl lithium is essentially, what is it? 1, 1, 2, 3, 4. This is Li, right? It's just a deprotonation, right? This grabs this, that's it, right? Then you get a carbanion, and technically, that's what I was saying. The lithium could coordinate with the carbanion instead. Essentially, you could think of it as a lithium hopping, right? But if he didn't mention it, don't really worry too much. I really just wanted to point out the acidity of protons in cyclic thioacetals, right? If you do have a proton there, whatever R group this is, this proton is acidic, right? Because the carbanion, the conjugate base, can be stabilized by the large cells of the sulfur there, right? Just the thing I wanted to mention there. But if it's not covered, don't worry about it. It's just I've seen it once on a previous exam. Okay, so what problem was this one again? We are using
I'm
ethylamine.
sorry. Can you go over that again? The one above it.
I said don't worry too much because if he didn't cover it, I just kind of mentioned it to see if he did cover or not, but he didn't, right? So don't worry too much, right? All I was pointing out is the acidity of the proton. That's it. Yeah, switch back to white. So here we have ET and H2. I don't know why they use like tosyl alcohol or whatever. TSOH. I mean, probably maybe this the reaction conditions are better using that. But it's really just an acid source. It's a proton source of TSOH. What else is here? And minus H2O. So once again, the Dean-Stark method. So starting off, I guess it doesn't really matter. Oh, oops. Second. Just wanted to make sure to get the, yeah.
I have a question about the minus H2O. Does that really, like, the minus H2O have a like a difference of like how the mechanism is gonna look, or it's basically H2O?
No, it just indicates that you're removing H2O to push it forward, right? So did he go over the Dean-Stark method?
I don't recall.
Anyone else remember if he mentioned Dean-Stark? He did, right? Oh no, somebody said he did. I don't know if that was in response to this. No. Okay, well, I mean, maybe he was going to mention it later. I guess I would assume when he finishes all this. The minus H2O is basically that when you have this reaction, these carbonyl chemistry reactions, it's just to indicate that you're pushing it forward. Because remember, one of the byproducts of all these reactions is water, right? Because water leaves, you know, the carbonyl, right? The original carbonyl that leaves as water, basically, right? So let me kind of, since this is confusing people. So let's say we have our carbonyl, right? We have, I don't know, say methanol, right? And we are in equilibrium with the acetal, right? And what the other byproduct is? Water, right? 2 H's from each methanol and the oxygen that was basically removed, right? So H2O, right? This is where the saying is basically if you remove water as this reaction is proceeding, right? So that's what the minus H2O means, right? If you're removing water, right, you are removing it from the product side because that's where water is in terms of the reaction, right? So if you're removing something from the products, right, that's where Le Chatelier's principle comes into play, is that the reaction, in order to keep equilibrium, will push it in the direction of whatever change you introduce to your system, right? So if you remove water, right, it's going to keep pushing the reaction forward, right? And this is when you're doing this kind of chemistry, right? It's what's something called, if you want to look it up, the Dean-Stark apparatus, where basically it's kind of like a sidearm tube or whatever, and it collects, you know, the water goes out through there, right? So then basically you get full reaction towards your acetal, right? Or whatever you're trying to create, amine, enamine, etc., right? But that's what the minus H2O is. It's just indicating that you are trying to make sure you get your product here, right? So the book includes it. If he doesn't really mention it, you probably don't really, it doesn't really matter. This is more of a, I guess, thing that's more important in terms of the lab technique, but the book usually always covers it. So that's why I always do it as well. And plus the problem was written that way. So this is TSOH, just in case. Same thing. It's a sulfonyl acid, right? Toluene sulfonyl acid. I forget the name. I think it would be toluene sulfonyl acid. But yeah, so it's just very acidic here, right? Because when this conjugate base, it's super, you know, stabilized from the sulfur, the conjugation, etc., right? So it's really just another acid, right? Okay, so here we'll start off. You guys said proton transfer is fine. I always prefer going that way anyway, so let's do that. But just to point out the reason why some people, you know, consider the amine to attack first is it's slightly more nucleophilic than alcohols, right? And that's why, you know, I guess Klein starts with that nucleophilic attack first, but it does not matter. And the reason, honestly, why I actually even prefer the proton transfer first is that we are in what kind of media, right? Are we in acidic conditions or are we in basic conditions? Acidic for the, I mean, the amine is slightly basic, and that's why, you know, people propose the other mechanism, right? But like for the most part, you're in slightly acidic conditions. So you're that's why I never really liked that one, because you form an O minus there and it immediately gets protonated. So you can't really say that the first step wasn't a protonation, right? It's hard to kind of disprove it. So anyways, let's protonate that OH. Get our baseball diamond there. Plus sign. Okay, now you have your nucleophilic. Let's do ET here. We'll do H2. Nucleophilic attack. And then boom, you get your what is it called? The carbonyl amine, whatever you want to call it. So O, this is N, this could be H, T, and one H up here, one H up here. And our baseball diamond. Okay, right. Now, what's going to be our next kind of set of steps here?
Is the final product the TSOH on the top?
Oh, my bad. I didn't even give you guys a file. I'm sorry about that. No, the TSOH is just the acid. Sorry about that. That might have been hell confusing. You're like, how the hell do we end up with that? No, here, the final product. Sorry, it's your amine.
Yeah, I
like
kind of
this.
panicked for a second. I was like, what the hell?
Yeah, no, that was just okay, so
Can we do the same thing here? Sorry, I'm just gonna like the intramolecular protonation deprotonation thing, like the two-step skipping kind of thing.
yeah, I mean, if everyone's cool with that, I'd prefer to do that just because it saves structures. But you know, in the sake of making sure I do it properly, I'm gonna just draw it all out. But yes, it wouldn't be wrong to do that, right? You could say it was an intramolecular deprotonation, right? And then you basically, you know, protonate your OH, kick it off, etc. Right? The only difference here, though, this is why amines, or well, actually, when we get to it, I'll mention it, which you know your professors probably already mentioned. Okay, so then we just have another proton transfer. I'm going to show both structures, but as someone mentioned there, you should be fine if you did it the other way. So H, baseball diamond. And then you have another proton transfer to protonate that group. So this is the carbonyl amine. That's the main reason I didn't want to just go directly with the internal proton transfer. So, oops. I guess a good way to probably test this would be to use a deuterated amine, right? And then if you had a deuterated amine, right, you could basically confirm if an internal proton transfer happened, right? Because then you could essentially just track the deuterium or do some other sort of kind of labeling, basically. And then you would just look for DOH, right? So that would be a kind of way you could confirm that, but it doesn't really matter. Okay, so what do we have here? This is now going to be OH2 plus. This is our okay, now we form our, remember the main thing here is you have a carbon-nitrogen double bond, right? And right, remember it was not shown all this time, but still technically there, right, is the lone pair. Well, actually, it comes after the second step. But so now, right, we reform our carbonyl as more. I mean, it's not really a carbonyl, but it's still we basically reform that double bond between carbon and the heteroatom, right? Except this time, instead of oxygen, it's nitrogen. So here and here, right? So now water gets kicked off. Minus H2O. And now this is the kind of main difference in terms of oxygen and nitrogen nucleophiles is nitrogen nucleophiles only add once, right? Just kind of remember that, what's it called? Oxygen ones, as we saw in all the examples above here, right? There's basically always a kind of double addition. With nitrogen, it only adds once, right? And it stops after that point. And then the main difference between enamines and imines, right, is really, right? So we have this, right, is when you use basically ammonia or a primary amine, right, you form imines, right? But if you have secondary amines, you get what's called the enamine. And the main difference is just really, if you just notice in terms of the mechanism, it's the last step. Is in the last step, you have a protonated, intermediate, right? And it's really the most acidic proton, right? So when you use a primary amine or ammonia, right, you have a proton directly on that N plus, right? So obviously that one is going to be the most acidic. And then, here we'll show a conjugate base, I guess. I guess we could just use the amine really, because that would probably be the most basic thing here anyways. ETNH2, right? It just deprotonates that proton. When we do an enamine, right, there's no extra proton here, right? Because there's going to be two R groups. So what actually happens is the next most acidic protons are at these positions, the alpha positions, right? And that's why you get an enamine versus an imine, right? It's literally because of that one proton, and that's why when we do an example of that, you'll see it a little bit more clearly. But this goes here, and then you get your final product, which is just your amine. I will answer your question in a second there. Boom, right? Technically a lone pair here. Okay, what's the difference between H plus and minus H? What did I do? Oh, sorry, I just didn't really put the plus, right? Thank you for pointing that out. Proton transfer. Yeah, I just forgot to put the plus in there. But those are all just proton transfers. I'll put those in parentheses. Okay, let's do an example of an enamine.
Wait, can you scroll up just a little bit?
Yeah, sure. Here, I'll just zoom out for you. Let me go find the problem.
Thanks.
I mean, all of this so far has been quite the same.
That's what I said. It's carbonyl chemistry. That's why, I mean, it's important for protection. And I guess the amines and amines are kind of functionally important. I guess people could use those. But it's literally the same thing. That's why I tell people it's not that difficult. It's just the same repetition, right? It's just literally, it's a matter of practice, right? That's why I just do a bunch of these mechanisms and I would go over them, but essentially it's the same. The most complicated ones are the carbon stuff, which is, well, you guys aren't doing Bayer-Villiger oxidation, which is, I mean, that's not really bad. It's the Wittig. That's the one that kind of really messes with people. You guys haven't learned that yet, so I can't really cover that. But I mean, I'll just cover it next week. That's not an issue.
No, cover it, please.
No, it's because he needs to show you the like in terms of, it's gonna take too much time to draw the intermediates, because basically what it is normally you would expect what's called Z alkenes to form, right? Because That's what you're kind of, things are, sorry, not Z alkenes, E alkenes, because they're going to be further apart. But one of kind of the cool features of the Wittig reaction is that you could actually, it's stereoselective, right? That you could actually get a Z alkene, right? And that's kind of has to do with like the electronic considerations of the Wittig reagent and stuff like that. So he's gonna like go into detail about like the different types of Wittigs and like, one thing it's called like the HWE reagent, all this kind of, and he'll probably, I don't know if he'll show you the actual like basically kind of 4-membered state you have there or whatever, but it's gonna take way too long for me to talk about that, because I like I said, I like to focus on practicing. That's gonna help you all do well. The theory and stuff, that's that's what our professors cover. But yeah, no, Wittig reactions are very cool. They're essentially cycloadditions. I mean, some people consider them cycloadditions. I think some people say it's something else, but very cool reaction though. In my opinion, probably the best not best, but like, yeah, this is the best reaction in terms of all of this stuff. Other stuff here is just like, I'm sure people have uses for them, but yeah. Okay, where were we? Enamines. I was still trying to look for a problem. I mean, I could always just make one. It's not like an issue. There we go. Okay. Damn. Okay, I'm just gonna modify this slightly. So this is 19.20, but I hate drawing 7-membered rings. So I'm gonna draw a 6-membered ring. So I'm gonna put 19.20A and I'm just gonna put star. Only difference I'm doing here is I'm just gonna make the 6-membered. H plus. It's so weird that like you could just notice this dude, the Klein, just gets lazier as he writes these chapters. Like in the beginning, he makes sure to write all the hash, and then eventually he's like, you know what? Let's put H plus. I always hate inconsistency like that. It's just better to just leave it as H plus throughout. Okay. Oh, this one, it doesn't matter. It's this one. I just realized it's a predict a major product question, right? But it doesn't really matter. We can draw up the mechanism. Okay. So it starts off the same exact way, right? Either up to you if you want to start off with the nucleophilic attack or the proton transfer, right? So let's start off with the proton transfer. Proton transfer. Okay. Now your amine here.
Is there a given final product for this one? Or is this just
Oh, well,
predict the
it
major
didn't
product?
actually give you because it wanted you to predict the major product.
Oh, okay, predict the major.
So, but we're doing the mechanism, so we'll figure out what the major product is as we go forward. Okay, so this next step, right, pretty straightforward, right? Just attacks there, right? And it's literally, like I said, it's just repeat. So if you get like a amine, acetal, or any of these mechanisms, or even the reverse, actually we'll do yeah, we have enough time to do examples of the reverse. So that way, if you get that as your mechanism questions, you should be able to do that pretty easily, I think. Like I said, it's just a matter of practice. And right, so we have OH here. I'm gonna have this, and then you have there. This is plus. Yeah. Okay. Once again, you could have skipped to this doing an internal proton transfer. I'm just going to do 2 for clarity. OH, now you have your carbonyl amine again. Yep. Now another proton transfer. It's 5, right? 1, 2, 3, 4. Yep. Now remember our lone pair there, right? We have same thing. Like I said, literally the only difference between amines and enamines is the last step, right? And it all has to do with the availability of a proton or not, right? So that comes in, you form your double bond, right? Water kicks off. Now we can draw this as the double bond. This is where that carbonyl was. Now notice this plus charge here, right? This is the main differences. Before, right? Remember, we need to make this neutral, right? Before there used to be a proton here, right? If it was a primary amine or ammonia, right? You have an extra proton available. But here, right, we need to get nitrogen to have a full valence, or not full valence. It should have a no formal charge. It has a full valence, right? So since you're in conditions that could still deprotonate the next most, acidic protons are the one next to that carbonyl, because remember, this is partially positive, right? This is kind of the chemistry of alpha carbons, which is chapter, I think, I want to say 21, right? It's because this is partially positive. You'd expect this, right, to be pulling this way, which would make these hydrogens partially positive, right? So those are acidic protons. So alpha protons is kind of a already, you guys should already know some of this by now, but kind of looking ahead, right? This alpha carbon, the alpha protons there next to carbonyls, they're going to be very important, because if you put them under very basic conditions, right, you could do all sorts of carbon-carbon bonding, right? And that's what's called enols, enolates, and all that chemistry, alpha carbon chemistry. Okay, so now we just deprotonate that, and it's literally just, what do we have? I guess we could just use the amine again. So this, right, it grabs that proton, this kicks in here, and that. It's still the same deprotonation. Now, the only difference is which proton, right, is grabbing a thing. So let me just zoom out here. What did we do earlier, right? Here, it was just the proton right next to nitrogen. That's simple, right? But here, right, you're still returning those electrons to nitrogen, right? It's just one more arrow because it's one carbon over. And that's why it forms the enamine, right? Because it's ene, right? En for the alkene next to the amine, right? That's literally the main difference, whether you use a primary or secondary. That's why you get slightly different kind of structures in terms of where their double bond is, right? So now you just get N. Alkene. It didn't actually matter which side you picked. Now I actually know why they probably why they probably picked the 7-membered ring for this question is because it could accommodate that alkene a little bit better. That's technically trans almost. I mean, it is trans actually. Yeah, no, I meant to pick one of the mechanism questions because I just wanted to go over the mechanism, and then I didn't realize it was the major product question, so that didn't matter, right? The mechanisms are the same whether you did 19.19 or 19.20. would be this. The only difference, as I was saying, is so what organic chemistry is. Really, the only difference is the kind of the skeletons, the chemistry, right? Chemistry is like, it's like eternal, right? It never changes. Just the stuff attached does. Yeah, so let's do, somebody said they wanted to do the Wolff-Kishner, right? So hydrazone. Oh, they didn't actually. Hold on, I want to find an example of this. Oh, perfect. 19.22. Okay. So predict the product of the following two-step procedure and draw a mechanism for its formation. This is going to be a long ass mechanism. But you know what? I'll let people try it, attempt to try it first. I don't know if you guys, I mean, the thing is the hydrazone formation, you know, I would assume, I don't know if you did the mechanism, because once again, it's just the same thing as all this other stuff, right? It's actually just like what would it be? It's just like the amine formation. The only difference is now instead of what's it called? NH2, like instead of a R group, it's just another amine. That's called what's it called? I forgot what the name of those are, but hydrazines, I think, actually, or hydrazane, one of those. So the first step in terms of, I'll give you a hint, is literally you could just follow the amine mechanism. The only difference is now here, let me just show you, is this, you could treat this as H2NR, right? That NH2 is just R, right? Before, what did we do before? We did ethyl, right? Now, instead of an ethyl, you just have an NH2 there, which becomes important in the second part of the reaction. And then the second part, we'll actually do that together since we didn't go over it. But the first part you guys should do now, because it's literally just like an amine. So KOH, H2O, and heat. He did this exact thing in class, this exact problem. Oh, but he did the first part, right?
Yeah, he did the first part only. The number one.
Oh, so you guys didn't actually get to, oh, I mean, whatever, it's fine. So yeah, just do the first part. Wait, did he use the same exact structure?
Wait, actually, he did the whole thing.
He did, wait, but was it the same exact structure?
No, not
or-
the same exact
Okay,
structure,
okay.
but he did the whole, even step 2 with the KOH,
Okay.
H2, and heat.
Yeah, I mean, okay, well, let's start off with doing the first step. We'll just do the second step together since, yeah, so I'll give you guys a few minutes to try that. Like
That's
I said,
also, that's a predict the major product.
this is, it says predict product and the mechanism. So I'm sure the mechanism is probably in the back as well, right? So it's kind of a two-parter question.
Gotcha. Thank you.
But I mean, I'll just tell you what the major product is here, right? Is essentially the whole point of this transformation, right? Is the first part makes your hydrazone. And the second part, what does that do? It's called Wolff-Kishner reduction. What does reducing mean?
Turns it into 2 H's.
Yeah, so in terms of like oxidation and reduction, organic chemistry, you could generally think of oxidation as more bonds to a more electronegative atom and reduction as more bonds to hydrogen, right? So really this whole process altogether literally just kind of chops this carbonyl off, and your final product, which I will give you since that will kind of help in terms of a mechanism, right, is just going to be this. So really it's great for if you have a carbonyl and you want to turn it into an alkyl group, right? So actually, if like, let's say you wanted to get this final product or something like that, right? And the only way you could have done it was probably, I don't know, through some carbon-carbon bond reaction that ended up having a carbonyl there, right? Then all you'd have to do is this Wolff-Kishner reduction, or you could use a thioacetal with rainy nickel, right? They both lead to the same thing, is that carbonyl is getting cleaved essentially and turning into two hydrogens. Though I don't think you guys covered the mechanism for rainy nickel. Probably just mentioned it, I would assume, because I don't think really the mechanism. Yeah, it's my favorite thing. I say it a lot too now. As I'm just reading really what it says. It's the rainy nickel is a nickel aluminum alloy, blah blah blah, and it says a mechanistic discussion for desulfurization is beyond the scope of this text. Klein says this so much, where basically just like I don't feel like writing about it because I don't consider it important for undergraduate organic chemistry. Which is BS because it's a text. I mean, I get it. The textbook's designed for undergraduate organic chemistry, but if you're going to write a textbook on organic chemistry, you might as well show everything, not just be like, hey, just accept this happens. I hate that. Okay, let's go over this. So first step, protonation. No, wait, no, we're just protonating right now. Next step is the attack. Okay. Now you have, write this. Each like this. Yep. Okay, that works. Nucleophilic attack, right? That is now going to be this OH, right? Now NH, H, and H2, right? Once again, instead of a ET or R group, the R group is just NH2, right? Plus, right? And we're going to go through 2 proton transfers or 1 internal proton transfer, right? And what are we missing here? Alkyl groups, right? Another proton transfer. That would be your carbonyl amine again. Brought this a little bit more left. OH2 plus NH, H2. What are we missing here? So the cyclohexyl, sorry, cyclopentyl, and it's a propyl group. Okay, so again, electrons come in, reformation of your carbonyl or carbon nickel double bond. Sorry, not carbon nickel, carbon nitrogen double bond. It's a little better there. There we go. And then we have our amine essentially. What this is called a hydrazone specifically, right? And what are we bonded to here? So we have our group this way and this group here, right? And now it's just another proton transfer, right? And you get your hydrazone, right? Which is more or less analogous to amine. The only difference is instead of a alkyl group, you have another amine connected. So just one thing I want to point out, right, is hydrazones, like this is the simplest hydrazone. But if you see something like H2N and like that, or something like H2N, which is hopefully you guys are seeing what happens here is, let's say this was ET and H, right? Which portion of this molecules are these hydrazines, right? Which portion of them are going to do the reactions or the chemistry with your carbonyl? Is it going to be, here I'll circle this, like these orange portions or the other portions, the pink portions? Look at it in terms of our mechanism that we just did, right? In the first one, we had NH2, NH2. So that's why I wanted to give these examples in case you see other types of hydrazine. People always get confused, like what the hell's happening? I've never seen that before. Chemistry is always the same though. So Serena said pink, Isabella said orange. We've got ourselves different opinions. So once again, what did I say? It was to treat one of the NH2 groups, right? Or one of the N groups as an R group, right? But the main reaction is happening with the NH2 group, right? That's why I wanted to give examples of hydrazines that are not just the simplest one, is because the one doing the chemistry here, right? So say this, match it, right? Is the orange part, right? This other N group can be any kind of amine, right? It could be that cyclic amine, it could be like ethyl, or it could be ethyl methyl, whatever it is, right? So the pink part there, right, is really just the other rest of the hydrazone, right? The NH2 part of any hydrazone, right? It's always going to be an NH2, right? It's the NH2 that does the chemistry, right? So this will be very clear, right? I'm just going to say this does hydrazone reaction. I should say part that reacts with carbonyl, right? Is the orange part, right? It's always going to be that NH2 part. And the rest of the hydrazine, sorry, will be whatever sort of alkyl group. But those can't do this reaction, right? Because the main thing you're trying to form is that double bond to N, like the imine has, right? And then this NR, so really any hydrazone, you could kind of think of any hydrazone as R, right? N, and then this could be, you know, NH2, right? Or it could be, you know, NRH or NR2, right? Any one of those, right? But the other part, that one other NH2 part, right? So really just for general things, it's gonna be H2N, N, and then I'll put this as N star, where N star can be either NH2, NRH, or NR2, right? But the chemistry happens with the NH2 group, right? In case you see structurally different hydrazones, at least hopefully now you'll know how to, you know, make sure you get what you did, right? Because I don't know why the book doesn't mention that. Because it always throws people off. They're like, yo, I've not seen that. I don't know what's happening, right? Like I said, if you just identify the parts doing the chemistry, you'll always get the right answer. Okay, so over here, right, is what's it called? Let me copy and paste that. So that's the end of part 1, right? So this is after step 1. Let me actually make a note of that. Copy. There you go. Now if we paste. Right. So let me just also write that up there. It was after step 1, right? So that formed our hydrazone, right? And then step 2 was the KOH, H2O, right? And this is the actual, I guess, what is it? Wolff-Kishner reduction part, where it's basically now what happens, right? I don't know actually if it would work with NR2s now that I think about it. Or the mechanism would be slightly different. It should still work. But basically, like the base, right, it interacts with the other nitrogen, right? And essentially what you're trying to create is a N2, right, which is going to be nitrogen gas, right? And that's what makes this reduction really, really good, and why it could, you know, occur really well is because you can just same thing. You can exploit Le Chatelier's principle. So I mean, let's start the mechanism, and then I could tell you what I mean by that.
Every time we see like KOH over H2O and heat, so that's always Wolff-Kishner, or is that
well only if you have a hydrazone, right? So you have to have this functional group here, right?
Okay.
Yeah.
So for other things, it would be.
It would. I mean, depends on what functional groups you have. You know, like KOH is a base, right? So if you had a, I don't know, alcohol or something like that, you could, you know, deprotonate it or do whatever. But when you have a hydrazone and you see those reagents, essentially you're reducing them, right? Yeah, I could zoom out for a bit. Hopefully that should be good. Actually, I don't know if this would work with the. It should work though. I'm pretty sure it should work. So actually, okay. So the first, so this part where I showed the other hydrazines, right? That's really just for hydrazone formation. I don't know if the Wolff-Kishner itself would work with the other products. So if you want to get those hydrazones, right, you could use all of these, right? So, but I don't know if they can be used for Wolff-Kishner. That's something I'll have to look up. But in case you get a question where, you know, you got like a NH2, right? At least you know how to form the alternative hydrazones, right? But in terms of Wolff-Kishner, I'll probably check and ask with Professor Biscoe or Boson if it's possible. I mean, let's start off this mechanism. So anyways, OH minus, KOH, whatever. I guess we'll just write OH minus just to be clear. I need to show off one of these protons right now. Right, let's do that. Right, it's gonna come. It's gonna grab it, grab this. I could just do this in one step, but let me just ship this first. Essentially, we're just gonna kind of break that double bond in. Which you'll see in a second here. Right, so now you have your amine, which is now basic, right? Nitrogen will want to create another double bond with nitrogen here, and essentially you kind of just have this, which is kind of weird if you think about it, but you'd rather have a nitrogen-nitrogen double bond. I guess that would be the kind of better way to look at it, to have a nitrogen-nitrogen double bond than a nitrogen-carbon, because this is going to be more polar. Here, this is going to be, I guess, non-polar, so it's more preferred, right? So that's why kind of this little resonance happens here. I'm just going to draw it as separate structures, but oh, sorry, I should use different colors. And oh, I forgot the rest of the structure too. Yep. Should be that way. Make sure very clear it's going on that carbon, right? Then we can just go on to the next one, which is just that. And then this is where the water comes in. It's just literally a proton source, right? Now we should have this and we still have another H here. The H like this. This is now a carbon ion that gets protonated. I guess I'll just show the protonation. You could write H here, H plus, but clarity's sake, I'll show the mechanism part as well. It's just going to be HOH and there, right? So now you installed one, what's it called? Hydrogen. So you've already reduced it once, right? So now we have this looking. And there, H, right? And then this is kind of where you're gonna see this in amine chemistry, right? But essentially this is gonna try to form N2, right? So basically your base is going to deprotonate that proton again. So let's write HO minus this way, right? It's gonna deprotonate this, right? This is gonna kick off here, right? I mean, I guess it depends on how you want to do it, but I would personally just say this proton, these electrons just go directly to where this triple bond will be. But I mean, I guess it comes down to whoever wants to do it, so it's whatever.
The
but
professor Bisco, Bisco showed it as like minus N2 with heat, like as the reagent. To
yeah,
remove
no,
this whole N2 part.
yeah, so the N2 hasn't left yet, but yeah, I know what you mean. Essentially, just gonna dissociate. So that's why I was saying basically an alternative pathway here would be instead of returning it here, you could just go this way, right? And then you get your N2, and then the next step would just be the cleaving of this to a carbon ion, right? Which would be just this way, and then N2 expels. I'll just stick to it this way, just so I could show the next step easily. I think the book does it similarly this way, but the orange pathway wouldn't be wrong. It still gets the same thing. And so now we have N minus, and sorry. Yeah, it's a very, very long mechanism. Okay, so you have N minus here, right? It wants to form a triple bond. It will be, then it will be N2, right? The good diatomic, very stable. And nitrogen is actually the best leaving group, probably. N2 gas, I should say, is the best leaving group in like all of organic chemistry, really. It's a gas. It's gonna be want to be expelled as a gas. So anyways, the next step should be this, and then I guess you could have another carbon ion to reduce. So this is probably where he wrote, I would assume, you have minus N2 gas, heat, right? Or if you heated this, right, the N2 gas would be expelled, right? And now you have your almost final product, which is a carbon ion. Looks like this. And that just gets protonated, right? So once again, I'll show that though, for clarity's sake. And bada bing, bada boom. You got your final product, which is literally all it is 2 hydrogens here. All that just to cleave a carbonyl. Yep. So really the only steps I would say that you could kind of do differently is really when this second deprotonation happens, you could have said that this could all happen in a concerted fashion. So let me kind of just show you the alternative pathway. I would say basically you have your deprotonation, this kicks here, and this kicks here. And then basically you can go directly to this structure. And this would just be minus N2 and heat. But I don't know if that is something they'll accept, or if that's how he did it. I don't know. It wouldn't be wrong though, because the main thing is your N2 gas is still expelled, right? So that's what I said. That's why all of these are proposed mechanisms, right? But I guess the reason the pink pathway here, so let me also just clarify this with the pink arrow too, right? Also the reason I'd say the pink pathway makes sense mechanistically is because you have the negative charge and everything, right? And most likely this wouldn't be a concerted action. I mean, if you have enough energy, it could be. You can't really say it isn't. But yeah, both those ways I think should work. You could ask him to confirm if that orange pathway I showed is fine. Might be some issues mechanistically, but I wouldn't see why not. Okay. Yeah, so that's where did we start from here? Oh yeah, we started all the way up here. That is the entire mechanism there. That's insane. So yeah, the only thing I guess I'll just add is I'm not going to do the full mechanism for, but this kind of where's the example of? There we go. Let's give an example of this. Okay, so hopefully you have everything there. Let's zoom back in, and let's go down here. And this is 19.26. Whatever, I'm just gonna leave it pink. Is so you have this, and now the first step, like I said, is literally analogous to cycloacetal formation, right? Which we did earlier. We did an internal version of that, but we still did it, right? So this just says predict the major product. And then the second step is rainy nickel, right? So after the first step, so let's draw both things. So after step one, what do we get? Oh, I missed some stuff here. What would we have here? Well, if this was oxygen, right, or acetals, let's say this was just the R group, right, we'd have two R groups here, right, OR and OR. Only difference now is we have this a diothiol, or whatever you want to call it, dithiol, right? So yeah, here now we get thioacetal, as Eric said, right? All difference here is that you have S and S, but the S are bonded to each other, right? So you have that. So this is the product after step one, right? And then after step two, right? What does the rainy nickel do? So this is why mechanistically, this probably isn't included, because most likely, right? Exactly, it's a reduction, right? Is you're probably gonna have something that looks like this. This is gonna be your nickel. Then you have the sulfur should be, I think it'll be directly coordinated with the nickel. And then this gets into the realm of organometallic chemistry. And then basically you have dissociation on the nickel surface, and then eventually you have hydrogenation occur, right? So this goes through a couple of processes, and essentially this gets one H, then it gets another H, the nickel complex gets removed, and I want to say the sulfur is hydrogenated as well. Yeah, rainy nickel is used for all sorts of hydrogenations, not just this actually, I'm pretty sure. So this whole process, if I think it's Mozingo or Rozingo, I forget. Someone can look it up quickly. I think it's the Mozingo reduction. That's what it's called. Funny name. That's why I forget if it's Mozingo or Rozingo, one of those. That's what this entire process is called. It's just how I was remembered it because the name was kind of funny, Mozingo. Yeah, Mozingo. Yeah. But rainy nickel, I mean, I'm sure you could look it up. It's used for all sorts of like hydrogenations and reductions. I think a lot of it is with sulfur-based stuff, but I'm pretty sure you could do all sorts of various reductions with it. So it's a very good reducing agent. But as far as you're concerned, I think the only time you see rainy nickel is in this case, which is this desulfurization here. But you could, I think you could use it for like what is it? Like nitro reduction and all sorts of various stuff. It's pretty I guess useful compound in terms of its ability to hydrogenate. Yeah. Anyways, your final product is just this, right? So whenever you see this combination of the thioacetal, right? The cyclic thioacetal and the rainy nickel, right? Just remember, it's overall a reduction. If you want to remember, you can remember the Mozingo reduction, and all it does is same thing as we did with the hydrazone, the Wolff-Kishner reduction, right? It's just all turning these into H's, right? So, okay. Really, I'll end down. I just want to do 2 problems. I'm not doing any more mechanisms. I think we've done our fair share of mechanisms.
Wait,
One,
so oh, sorry. So when you see sulfur thiols, it just turns them into the H's whenever radium nickel is exposed.
yeah, so only if you have radium nickel, right? If you just have this by itself, you get product 1, right? And that would be your answer. But if it's the combination of both steps, then your final answer is the one next to 2 there, right?
That's only for like the sulfur thiols when you have radium nickels that you'll get the 2 H's, or is this for like you'll get the 2 H's for anything?
As far as you're concerned, it's only when you see the thioacetals. Like I said, it can be used for a lot of different stuff. I'm pretty sure thiopenes, a variety of different sulfur-based stuff, and also like nitro groups. And I want to say it could reduce benzene as well, aromatic. Just it could do all sorts of hydrogenation, radium nickel. But as far as you guys are concerned, right, the only thing you're going to see it for is for the thioacetal, right? Okay, so let's do, this is kind of what I was alluding at earlier, was 19.23, right, which is products you expect after kind of hydrolysis, right? So remember the whole point of that like minus H2O thing was to push the reaction forward. And I think I mentioned, I do this count right? Yeah, okay. I mentioned that, second, there we go. That if you just introduce water or hydrolyze them, right? Essentially just do, some sort of hydrolysis, right? In this case, it's H3O plus or whatever, right? You're literally just going to just break up that group, right? So identifying those groups might be important because if in case you're giving a question like this, right? Then you're like, I don't know what the hell's happening here, but just remember, this is literally the reverse of everything we just did. So all you have to identify is really where the carbonyl was. And that's why I was saying the OCOs, the N double bond, the enamine bond like this, right? That's where all the carbonyl was. So here, I guess I'll label some carbons for y'all, and then you could tell me where the carbonyl originally was. So B. Eric, does everyone agree? I think so, right? So if we were to draw this over this, right, you could do this. This is where our carbonyl is. We cleave this, right? So our original compound, let's use a different color, would be first the pentanone, I guess it would be, right? And then the other technically side product would be that diol there, right? So hydrolysis, if you see a question like this, maybe since we're still going to be doing 19 next week, I'll do a reverse the hydrolysis mechanism as well, because kind of just want to do quick practice problems. So let's do a couple of more ones. Oh, okay. Okay, let's do B. And there. Then we have C. Right. What's another one? What's another one? D. Yeah, let me zoom out a little. You could try the rest of this problem too. What was this? 19.23. It's a good problem. Where is it? So this is a bicyclic. And then this is NCH3 2. So it's a secondary thing there. So start with the first one. Say A, B, C, D, E. Where was our carbonyl? Oh, yes, the reagent. I should mention that. We're doing the same thing. It's just H3O plus for all of them. Right. We're doing hydrolysis of all of these. So yeah, Eric said C. Does everyone agree, or does anyone have another position?
I'm kind of lost. How are you guys
So
saying?
you have to identify where that imine came from. So it's literally, this is a question that might come up on your exam doing this reverse thing. That's why I'm saying identifying those functional groups is important, like whether it's OCO, right? You have N double bond or N like this, right? This is all originally, this was the carbonyl like this, right? Or you could say, yeah, this was the carbonyl. This was the carbonyl. This was your carbonyl, right? That's the original carbonyl. That's how it looked like, and then whatever else is attached. So that's why Eric and Mohammed there said C, right? And if we had a carbonyl this way, right, that would make sense because now we would have it's like this. We have 1, 2 there, and then the original amine was methylamine, so it's just H2 NME, right? Methyl, right? And if we did this reaction, you'd get that product. This is why I was saying being able to identify those centers there, right, is important if you were asked a hydrolysis question, right? Knowing, this could also be a mechanism question, right? Which we'll do one example of to start next week. Yeah, this is literally the reverse of everything we did, right? Because remember, all that stuff's in equilibrium. So what about C here? Yeah, we'll label a couple carbons here. A, B, C, C, right? Now, what was the original? This is where you have to be careful. What was the original? Because if this was C, right? The kind of you could think about this as is this was 2 H's like this, right? So let's be careful in terms of what the R groups. Here, both the R groups are H's, right? Here, the R groups were this one and this one. And the first one, the R group was just this entire cyclopentyl ring, right? Here, the R groups are H's, right? So this actually came out of formaldehyde, right? And then your other thing is your cyclic acetal, right? So for those who might be getting confused, right? Like I said, just practice this in terms of identifying this groups. So this was actually our original carbonyl, right? This is where it's kind of important to see what the R groups are there. What ketone would it be? There's no methyl or ethyl groups there. It wouldn't be a ketone, right? Because let me maybe draw this out a different way for everyone else who might be just as confused, right? If we drew it like this, and then what's the rest of the structure? This. That's the structure, right? So in the first example, we had something similar, right? Make this clear, right? We had this cyclopentyl or whatever it was, right? So that means a carbonyl, it's easy to kind of see, right? The only thing here now is those R groups, right? These are H's here, which means the original thing was formaldehyde, right? So that's why I was saying identifying that OCO, right? Once you identify the OCO, anything, the R groups, whatever they might be, that's the original carbonyl, right? Those could be both H's, it could be one H, right? Doesn't matter what it is, but that's the original carbonyl. So this actually came out of formaldehyde, right? And the rest of the structure, let me move this to the side, is your cyclic acetal, cyclic diol. So the rest of the structure would be OH, OH, this. And then all you did was you, remember, we were trying to make this bond, right? That's where it came from, right? So, like I said, do a little practice with this. Here, let's do a couple of carbons, say A, B, C, and D. So B, right, same thing, identifying that enamine group, right? If this is the enamine, that means the original carbonyl, right, was, and let's say this is whatever R is here, right? Then the original carbonyl would have been R like that. And whatever R is here, whatever's R is here, right? So you could overlay it as, I'm gonna remove B here, but this was the original carbonyl. So now if you drew it, right, we have, oops. That, and then we just have the carbonyl coming this way. Oops. And then we have, what was it? So we had dimethylamine. So Me2NH, right? And if you did this whole process, you would see you got that enamine that looked like this. Right? So that's what I was saying, identifying those groups. And I've repeated that same line like 20 times now, but like it's important. It could literally, get your answer real quick, right? And maybe you might also get a mechanism where you have an acetal, right? So try the rest of this problem, 19.23, if you're having difficulty. And I'm sure the answer key probably draws a little better diagrams than I do, right? In terms of how to identify those, right? So, okay, so the last thing we're gonna do is really just a kind of ranking question, because I saw this earlier, and this is one of his suggested questions as well. So we're gonna end here, right? And it's basically asking you for each pair of the following compounds. So let me draw them all out. This is actually one of your recommended questions. Oh, oops. And this might be something you get or something similar. Though once we learn, what is it? Acyl chemistry, this question might change a little since this is kind of limited to aldehydes and ketones. So this is CH3, this is CH3. And for similar purposes, I'll label this as CH3 as well. It's the same thing if I remove those CH3s, right? So it says for each pair of, oh shit. Okay, this makes a lot of sense. All right, so it's not all four. Okay, I was about to say it's going to be kind of hard to compare all four. Okay, so this works out then. So, oops, we have A, right? And then we'll do B on the side here. So for each pair, it says identify which compound will be more expected to react more rapidly with the nucleophile, right? So essentially what it's asking you really is which one is more electrophilic. So this is kind of a question you might see on your like exam is like rank the followings in terms of electrophilicity, right? So between the first two, you have a ketone and an aldehyde, right? So Ali there says aldehyde. Does anyone agree or disagree? Agree? What's the reasoning? Why is it more reactive? Right? We know it's more reactive, but why? So that's one, right? So more partial positive charge, right? You could think of it that way. So there's two ways you could take it, basically electronic and steric considerations, right? So we'll draw both of those out. Is here, right? You have essentially you have CH3 here, right? So this kind of carbon, right? It's full of electron density, right? So in terms of kind of the CC bond here, right? You would expect this not to be very polar, right? I mean, obviously we could label this as partially positive, right? Right, but like between C and C, right? If anything, this can kind of donate a little bit of electron density into the ring, right? That would be through hyperconjugation, right? So when you have alkyl groups, right? They're weak electron donating groups. So the same thing kind of applies here, right? Is that this is not going to be very partially positive compared to something like a carbon-hydrogen bond, where we know carbon is more electronegative, right? So we could kind of put this as plus. I don't want to put plus. I put like plus 1.5, really, right? It's slightly more electronegative, slightly more partially positive because of that carbon H bond difference. And then the other way you could look at it is in terms of, so the phenyl groups are the same on both, right? So you don't really compare that side. The other way you could kind of think of it is in terms of electron density, right? Where you have, these are the clouds of electron density, right? And here you have just, this is the CH3. This is your H, right? So in terms of a nucleophile trying to attack this, right? We went down one way, right? It's going to have to get past, right? That giant cloud of electron density. So sterically, this is more inaccessible in a ketone, right? Here, it's only a hydrogen. It could easily access the hydrogen. I mean, it could easily go past the hydrogen. So you could explain it two ways in terms of sterics or electronics, right? Both will be acceptable, and both together is even better, right? You could say sterically, the aldehyde is less hindered, or it's more sterically accessible, right? And then electronically, it will make the carbonyl more partially positive because the CH bond is more polar than the CC bond, right? Both answers are acceptable. And then for the second one should be a lot simpler, right? You have CF3s versus CH3s, right? So CF3, as one person said, hopefully everyone agrees, right? If I was to draw this out, this would be purely electronic considerations, more or less, because this, right, we could as reference, we could put that as partially positive, right? Now here we have F. So these are all partially negative. Fluorine's the most, right? It's going to make this carbon very partially positive, right? And we have basically two of these, right? Right, both pulling on this. So you could say this is like plus, right? The inductive effect, right? You could kind of use that REO stuff, that the CF3 groups have a greater inductive effect, right? Therefore, withdrawing electron density from your carbonyl carbon, making it much more electrophilic because of electronic considerations, right? And that's it. We'll
Wait,
do
I have a
some more.
question.
Yeah.
So you're saying that the one with the CF3 is more reactive with a nucleophile?
Yeah.
But I'm just confused with, because this is more sterically hindered than the CH3, or is it the same?
Well, yeah, fluorine is going to be slightly bigger, right? But that center is so so like electron poor because of the CF3 groups, right? That's why this it kind of overrides your steric considerations, right? It's just so electron poor that a nucleophile can easily find it, right? So yeah, if you think about, that's why I was saying sterics isn't really a consideration here, is because yeah, the CH3 groups we could consider like this circle, the CH3 group. The CF3 group will be slightly larger, right? It would be like that. Maybe that's a little too large, but you know, it's like this, right? So yeah, they are, you know, bigger, right? But there's so much more electron withdrawing, right? So let me explain this again. Ex Carolina asked, right? So if you just compare them, right, normally, right, let's consider this, you know, acetone here, right? That's what we have. We'll consider that this carbon here as partially positive with a 1+, right? So that's kind of our standard, right? Now, if we look at it in terms of inductive effects, right, the CH3s don't really have any inductive effects, but the CF3 groups, on the other hand, right, all these fluorines are electronegative, right, which makes the carbon here very electronegative. I'm sorry, electron poor, right? So we could consider this plus plus, consider this plus plus, right? And both of those electron poor carbons are pulling on a carbonyl, right? Which means it's withdrawing even more electron density away from the carbonyl, right? That's just the inductive effect, right? You have electron withdrawing groups next to something that already lacks electron density. So it's through the inductive effect, it's gonna literally pull even more electron density because fluorine wants to be electronegative, right? It wants the electrons, right? And that would make this extremely partially positive. So electronically, the CF3 one, right, is going to be much more electron poor than the CH3 one because you have powerful kind of electron withdrawing groups attached, right? So the electronic considerations really kind of bypass any sort of steric interactions you might have, right? Because remember, it's a charge attraction, and if you have a very big difference, essentially the LUMO of this, if you look at it in terms of molecular orbital theory, the LUMO of this is going to be a very, very excellent LUMO because it's very electron deficient, right? And then nucleophile will have a very good HOMO-LUMO interaction with this one compared to the other one, right? So yeah, it's purely electronic, right? Electron withdrawing groups make things, electron poor, right? If something's electron poor, it's going to be, in the case of being an electrophile, it'll be a better electrophile, which means if it's a good electrophile, a nucleophile will be more likely to attack, right? Hopefully that clears that up. Anyways, we're going to end there. I guess probably next week we'll probably just do 20 and 21, hopefully. I mean, you guys should probably be finished by next week, the rest of 20 and 21. 21 is a lot of repetitive shit as well, too. Sorry, not 21, 20. So 19, you should finish the rest of 19 and then 20 all of next week as well. Like if you go to the review of reactions for 20, you're going to see a bunch of reactions, but they're all more or less the same, just different derivatives have different reactivities. Yeah. Have a good rest of your weekend. I will see y'all next Saturday.
Thank you, Sharu.
Yep, no problem.